Good afternoon, everyone. Today we are going to start a new lecture, proof techniques. We will cover 4 different proof techniques in this module. First one is direct proof, and then we have proof by contradiction, and then disproving, and then proof by mathematical induction. In today's lecture, we will cover direct proof, methods of direct proof, and counter examples. And you will need some knowledge from your previous lecture to solve the problems in this lecture. The predicate statements, predicate logic, that one. Okay. So what we will look at is, first, I'll introduce you to the fundamental or prerequisites that you need to know. For example, definitions of different types of numbers, different types of integers, and then how to write proofs, the proper way of writing proofs, and then we will look at rational numbers and how to use the definition of rational numbers to write down proofs or prove some statements, universal existential statements. And then divisibility and floor and ceiling function lastly. We will look at these 1, 2, 3, 5 things in today's lecture. So before we start the topic of proof, we need to know some assumptions. Okay, there are this is from your book. All of you should have access to the book that the name of which I uploaded on My Times. Most of your lectures and tutorials are taken from there. So same is the case with this. The assumptions that you need to know before you start writing proofs are, first one is that you should know the basic laws of algebra. For example, commutative law, associative law, distributive law, all of those you can find in Appendix A of your book. I will show you in the book also where you can find them. But you should be familiar with the basic algebra, laws of algebra, and then 3 properties of equality. First one is for all objects A, B, and C. The first property of equality is that A is equal to A. Second property of equality is A is equal to B, and then if A is equal to B, then B is equal to A. Third one is if A is equal to B, if you know that A is equal to B and B is equal to C, then A is equal to C. So these 3 properties you should know as a foundation, as a basic knowledge. And then principle of substitution. If we have 2 objects or 2 elements A and B, and we know that A is equal to B, then we might need to substitute B in place of A or A in place of B when writing proofs. So these principles you should know. These are the assumptions, okay, you should know before you start writing proofs. And then, because we will be mostly dealing with integers, so the concept that there is no integer between 0 and 1. Who knows what integer is? What is an integer? Whole numbers, yeah. So we will assume that there is no integer between 0 and 1 because there is no whole number between 0 and 1. Okay? So that you should know. And that the set of all integers is closed under these 3 operations: addition, subtraction, and multiplication. What does it mean? That the sum of integers is an integer. Difference of integers is an integer. Product of integers is an integer. Okay. For example, if you have 2 integers represented with some variables, if we add, let's say R is an integer, S is an integer. If we add these 2, we will get some integer. The answer that we get will be an integer. If we subtract these, then the result will be some integer. If we multiply these, the result will be some integer. Okay, this is what it means by the 4th assumption that we will keep in mind, okay, when writing proofs. So these you should know. Now I will show you, and I have pasted one example. There are some axioms and theorems from your high school, okay, that you need to know. I will show you in the book as well. This is the first book that you can find on, not the book, but name of the book you can find on My Times. If you go at the end of the book, you have two appendices. Appendix A, there you will find all the properties, laws, and theorems, okay? These you need to know when writing proofs. Now we will start with definitions of some common types of integers, because they will be the base for writing proofs. You will start your proof from the definitions of whatever types of integers are given to you. You will first identify what type of integer is given to you in the statement that you have to prove, and then you will need to know the definition of those integers in order to continue writing the proof and then prove it, okay? So 4 common ones are even integers, odd integers, prime integers, and composite integers. So definitions, we know what even numbers are, what odd numbers are, prime numbers are, and composite numbers are, but you should know how to symbolically write them. So even integer is, I'll first go through the definition. An integer n is even if and only if n equals twice some integer. How do you represent it symbolically? Twice some integer. It can be any variable. You can take any variable over here, okay? But this is the definition of even integer. Then the definition of odd integer is, an integer is odd if and only if it equals, if an integer is, if n equals twice the integer plus 1. So odd integer definition is twice some integer plus 1. So these definitions you should know, because they will be the base of writing proofs. You will start your proof from here, okay? Then there are some properties of even and odd integers that you need to memorize, and you might be given these properties to prove, and I will go through these 7 properties. The sum, product, and difference of any 2 even integers are even. These are established properties, but you might be given one of these to prove, okay? Then sum and difference of any 2 odd integers are even. The product of any 2 odd integers is odd. Product of any even integer and any odd integer is even. The sum of any odd integer and any even integer is odd. The difference of any odd integer and any even integer is odd. The difference of any even integer and any odd integer is odd. These are some of the properties of even and odd integers that you should know, and you should also know the definitions of odd and even integers to prove these. We will look at one example of how to prove them. First we will look at the next types of integers, prime and composite. What is a prime integer? Yeah, yes? What is a prime integer? Anyone? Yeah? Yeah. Yeah. Yes, correct. So how we will represent it symbolically? First thing is, an integer n is prime if and only if n is greater than 1. It means all positive integers greater than 1. And for all positive integers r and s, because we need two numbers, because these will be our factors of the prime integer. If n is equal to rs, then one of them is equal to n. and automatically the other, based on the definition that the student told, based on that, one of them will be equal to n, means the prime integer, either r or s, and the second one will automatically will be equal to, if r is equal to n, then s will be equal to 1. If s is equal to n, then r will be equal to 1. Okay, so these will be the factors, these two will be the factors of prime integers. So definition and condition you should know. First thing, n will be greater than or equal to 1, means the prime integer will be greater than or greater than 1. Okay, and one of the factors will be equal to 1, and one of the factors will be equal to n. Okay, so these two things you should know for the definition of prime integers. And like even and odd, they are complements, like they are kind of opposites. Similarly, prime and composite, they have the similar relationship, so it's opposite of that. Here in composite, what you will have is that if r and s are factors of n, then r will be less than n, which will be the composite number, and greater than 1, and s will be less than n and greater than 1. Okay, so these are the definitions of prime and composite that you should know. Again, you will be using these conditions and these definitions to start writing your proof. Symbolically, how do we write for the prime integer? For all positive integers r and s, if n is equal to rs, then either r is equal to 1 and s is equal to n, or r is equal to n and s is equal to 1. Is it clear? Clear? Do you understand? Okay. For composite, there exists positive integers r and s such that n is equal to r, the product of r and s, and these conditions are met, that r is less than n and greater than 1, and s is greater than 1 and less than n. So these are the definitions of prime and composite integers. So we have what we should know as foundational knowledge, the 4 assumptions, definitions of odd, even, prime and composite integers. Okay, and then also how to write existential statements, universal conditional statements, and the rules for these to be true and for these to be false that we covered in our last lecture. These will be the foundational knowledge, the prerequisites to start writing proofs. So what is the rule for an existential statement to be true? What type of statement it is? This statement, what type of statement it is? So when is an existential statement true? The rule for that is? Yeah. For that, the property or the predicate, it must be true for at least one value of x from the given set of numbers. Okay. So this will, it means that to write a proof, we need to find at least one such example. Okay, for existential statements. For now, we will first look at how to disprove universal statements before looking at proving universal. How can we disprove a universal statement? Yeah, we need to find one value of x that makes the predicate or the property false. Okay, and what that value or what that example is known as? Counter example. Yeah. Okay. Next, we will look at how to prove universal statements. So what is the rule for proving universal statements? It should be the predicate or the property should be true for all values of x from the set of numbers. Okay. Now there are two methods to prove universal statements. One of them we have covered in last lecture, that let's say some predicate is given to us, and first method we prove, let's say this is for universal statement, and we prove this by plugging in all the values of x given to you. Okay, that method, plugging in all the values of x given to you in the predicate. All right, that method is known as, it's an exhaustive method, right? So this method is known as method of exhaustion. You are going to show that the predicate is true for all the values of x. For example, this was the range for this, up to the largest number. So this method is known as method of exhaustion, but this is not suitable. You may have numbers greater than 2600,000. How will you prove then one by one? So to solve this issue, we have a universal generalization method. I'll first go through what the concept of universal generalization is. To show that every element of a set satisfies a certain property. Now, what does it mean in terms of universal statement? Let's say this is the universal statement. Then this is the element, and this is the set of numbers. Okay, it satisfies a certain property. Suppose x is a particular but arbitrarily chosen element of the set, and show that x satisfies the property. So simply what does it mean is, we know the general definition of different types of integers. We use that definition to prove the statement. Simply this is what it means. Okay, so we use the general definitions, the general formula of the integers, different types of integers, to prove a statement for any given value of x, or any variable or any element from given set of numbers. Okay, instead of just going through from starting from first value, then going through each value one by one, we just use the definition of, let's say in the statement we have to prove for even integer, we will simply take its definition, its symbolic representation, plug in the value, and then prove it. Okay, so that is what it means. Okay, universal generalization. Is it clear? Clear? Okay. So this generalization method leads to method of direct proof. Direct proof simply means you simply take the definition of the types of integers, whatever is mentioned in the statement, and take some steps, prove the statement. Okay, you don't use any other method like contradiction. You make the contradiction first, or use some other complex method like mathematical induction, or disprove and then prove. No, you straightforwardly, what you do is that you take the definition of the integer. So you should know the definition. Okay, you should memorize, and then you start from there, take some mathematical steps, and prove your statement in the form of the integer that you have been asked to prove. For example, if you have been asked to prove that certain integer or certain expression or equation is even number, then it means that you have to show in your proof that it is in this form. You have to prove it in this form. If you have to prove a statement to be an odd integer, you have to prove it to be, you have to show it in this form as a proof. Okay, so direct, you take the definition, plug in the values, or use a substitution method, and there are some other methods also, we will look at those, and directly prove the statements. Okay, so what is the method of direct proof? First, there are two ways in which the statement could be given to you. One is simple proposition, and second is it is in the form of a quantified statement, a universal statement, or an existential statement. Let's say it is given to you in the form of a simple proposition like this. the thing that you need to identify is the starting point. In this type of statement given to you that you have to prove, the first step is identify the starting point. Second step is identify the conclusion that you have to show, means the part of the statement that you have to prove. So what it means is that you have to identify the hypothesis part or the assumption part, and you have to identify the conclusion or the part that you have to prove. Okay, means restate this simple proposition in the form of a universal or a quantified statement if simple proposition is given to you. If the statement is given to you in the form of a quantified statement, there what you will have to do is a few main steps, requisite steps that you will need to show when you are writing the proof. Okay, let's say straightforward you are given a quantified statement. Now here what you have to do is simply, mostly when the quantified statements are given to you, the hypothesis and conclusion part is already stated. Here what you will do is you will assume the hypothesis to be true. You will see what type of integers are mentioned over here. You will write them down in the form of their definitions, and then you will use these to prove the conclusion. So you have to show the proof for the conclusion part. You will start from the assumption, take the definitions, use those definitions to substitute in the conclusion part, and then prove that conclusion. I'll show you through an example. And main steps that you need to show are that, now here you see what you are doing. You are taking the definitions, right? From the hypothesis, you are taking the definitions of the types of integers. So you have to write down by the definitions of even integers, odd integers, whatever mentioned in the hypothesis. That is one thing, first thing that you need to show in your proof. Second thing is, I told you that you will substitute these in the conclusion. So you have to show the substitution. These are the blanks. I will just mention them over here by substitution. So you will be substituting the definitions of whatever types of integers are mentioned in the conclusion. Next thing is, it's up to you. This is the next step after substituting is about your mathematical creativity. You have to take the steps, okay? It's up to your knowledge, mathematical knowledge. Depends on what type of values or what type of expression you get. And for this particular example, because we are dealing with even and odd integers in both the hypothesis and the conclusion, so a common step that we take in proving the odd and even integers is we factor out 2. Why? Because in the definitions of both odd and even integers we have 2. In even we have twice some integer, in odd we have twice some integer plus 1. So we factor out 2, but this is the case for even and odd integers, okay? And after that, these are some of the main steps that you have to show. First one is definitions of the types of integers. Second one is substitution. Third one is this is specific to the types of integers. So the third one is that you assign some variable to the, when after you factor out whatever you are left with, all of these are integers. This is from your assumption that the sum of integers is integer, difference of integers is integer, product of integers is integer. Okay, so we know that m is integer, n is integer from the definitions, right? So we can assign it to some variable to simplify it, to show it in the form of, in this case, even integer. So we can assign it to the whole expression to some variable, where we will then explain that whatever variable we are using to enclose or to assign it the expression to, that is also an integer. Okay, why? We have to state the reason. Okay, this also you can find in your book. I'm just writing it over here. You have to show this step, that in this case, for example, we assign this expression to integer t, then t is an integer because m, n, 3, 2. 3 is an integer, 2 is an integer, 1 is an integer. And m and n, we have already shown they are also integers. Okay, so, and 1 are integers, and because the sum of, what you will explain over here in this blank, because sum of integers is integer. Okay, so this is the third step that you need to show. Whatever you have over here, if it is, let's say if it was, you don't need to simplify it further for this example. You can simply assign it to a variable, and then let's say it was like this. So in this case, let's say this was the expression we were left with after factoring out 2. So in this blank, what you will write is, because the difference of integers is integer. If it was, let's say, product, then in this blank, what you will write is, because the product of integers is integer. Okay, depending on what you get within the brackets. Okay, this will be the third step that will need to show. And then lastly, this will be the conclusive statement. Hence, whatever expression you get, by definition, this is integer, even integer, whatever is whatever you have to prove in the conclusion. We'll look at an example from start to finish. Let's prove the first one, that sum of any two even integers are even. So now here, this was the example that I told you about, that you might be given a simple proposition. How do you start writing proof for these simple propositions? Here you are given simple one. Okay. So the statement that we have to prove is the sum of, what was it? Any two even integers is even. First, try to restate it in the form of what type of quantified statement it is. You'll identify from the keyword. This we covered last week, that you have to look at the keywords to identify what type of statement it is. Any, so it means it's a universal statement. So for all, you can say, you can assign, because we need to have two integers, so you can take for all integers r and s, you can take any variables. If r and s are even, then you can write their sum, or you can write r plus s is even. Okay, so first restate your proposition in the form of a quantified statement, identify what will be the hypothesis and what will be the conclusion, and then start writing your proof. To start writing proof, what was the hypothesis? Yes, what was the hypothesis? If r is equal to even, take the definition, and s is equal to even. What does it mean? Take different variables. Okay. Then is equal to what? Even, right? This is what you have to prove. What does it mean? That you have to prove it in this form, twice some integer. Okay, so you will show your proof in this form. Now from the hypothesis you will start. Suppose the first step, what will be the first step in the previous example that we covered? We are done with the first step. Now, by, what is the first step? What will we do over here for substitution? Yes? Yes. By, so this is the first thing that you have to show. By definition you can write, and next step is by substitution and then simplify. Now because we are dealing with even integers, I told you what you do is you factor out 2. What you are left with, this is a very simple example. We know this is integer, we know this is integer, right? So the sum of these will also be integer. We can simplify it. Let k plus t is equal to x, where x is some integer. Then r plus s is equal to what? Okay. So this is thus, this is proved. Okay. This is how you prove. This is a very simple example. This is how you show the proof. So main steps you have to show. The definitions, the substitution in case of even and odd integers, factor out 2, and then assign it to some, whatever you have in the brackets, assign it to some variable, and give the reason. Okay. From the assumptions, you need to know the assumptions. From the assumptions, give the reason. From the definitions of the integers, give the reason, and then simply prove it in the form of the type of integer that you have to prove given in the conclusion. Okay. So in the conclusion, you had to show that sum of 2 integers was even. You know the definition of that is this. Okay. So you have shown it in your conclusion. Okay. Yeah, these are the main side notes that you have to write. Yeah. Is it clear? Clear? Understand? Yes? Okay. Okay, here we have one more example. It's already, I'll go through it. Another property of oh, this is the same thing that this is the same one. We will do another wait. Okay, we will prove another property later on. Let's first go through how to write the proofs properly. Let's first go through that, then I'll come back to proving other properties. So common mistakes that you have to, before writing proofs, I have already told you how to write down the proofs. So common mistakes that you must avoid when writing the proofs is, first one is arguing from examples. Means don't plug in specific values for the integers. Okay. Take the definitions. Like for example, if you have to prove that r plus s is where r is even, you are given, and s is also even, and you have to prove that r plus s is even. Don't just take r is equal to even, so you take any number, 2, 4, or don't do that. That is not the correct way of proving. And then you take any value for s also, it is even, so you just take any even number. And then you prove it, just simply add them and then prove that r plus s is. This is incorrect. Don't do that. Use the definitions. Okay. Show them in the form of the symbolic representations of the definitions of integers. Second is, another common mistake that students make is using the same letter to mean 2 different things. I told you Okay. Second common mistake is that using the same letter to mean two different things. I told you to take different variables to show the definitions of even integers and odd integers. I mean, even if you have same integers or you have different integers, use different variables because of the concept of generalization, that you select any element from the given set of numbers, any arbitrarily chosen element. Okay, so that is why you have to use different variables for different integers that are given to you. Let's say, for example, the sum of any two even integers. So it's, if your first even integer is r, you will use a different variable because this is specific to sum. And then let's say the second one is also an even integer. You will use different variable because this is a different integer from the second one. Okay, that is why you will select different variables to represent the integers given to you in the question. Then jumping to a conclusion or assuming what is to be proved means you simply let's say this is what you have to prove without, for example, this is a specific case of even and odd. So without factoring out 2, without showing this step, or without showing the step in between these two, like for example, without showing this, without factoring out 2 or whatever is in between, because this is a simple example, so you don't have any mathematical step in between. But let's say you have a complex expression and you need to maybe add or factor out other things also, other values. So without showing those, you simply jump to this conclusion. Don't do that. You have to show the main steps. So this is what it means. And you have an example over here how to write proofs correctly, and I have also shown you through this example that I solved for you, this one. So at least the main steps that you have to show is, if a simple proposition is given to you, I will recap. If a simple proposition is given to you, you have to restate it in the form of a quantified statement. Identify the keywords. From there you will know what type of quantified statement it is. Then identify the types of integers given to you in the hypothesis part. Identify the type of integers that is given to you in the conclusion that you have to prove. Then take the definitions from the hypothesis, substitute those in the proof, in the conclusion, and then take the next mathematical steps. And after that, based on the definitions, show the proof in the form of the type of integer given to you in the conclusion. So these are the main steps that you have to show when you are writing proofs using direct proof method. Is it clear? Okay. Next, we will look at rational numbers. So we are already done with even, odd, in prime and composite. Now we will look at the how do we represent rational numbers symbolically. So here a real number r is rational if and only if it can be expressed as a quotient of two integers. So keep these keywords in mind. A real number is rational, a real number, if it can be expressed as a quotient of two integers with a non-zero denominator. What does it mean? Let's say r is a real number if it can be expressed in this form, in the form of a ratio or quotient, where the denominator is non-zero. Okay, then that is a rational number. And if we cannot show it in this form, its complement is irrational. Okay. Next, we will look at, just to show you examples, are these these numbers rational or irrational? Is it a rational number? This one? This? 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 Yes, because you can write it in this form. This? No. Why? Because denominator is 0. It goes against the definition of rational numbers. Okay. Now let's jump into the how to prove a property of rational numbers. A property is given to you of rational numbers, and you have to prove it. So the main steps will remain the same. Means if a proposition is given to you, restate it in the form of a quantified statement, identify the starting point, means the hypothesis, and then identify the conclusion. That is what you have to show the proof of. Okay. So any sum of rational numbers is rational. This is the property. To restate it in the form of a quantified statement, first you have to identify what type of quantified statement it will be. You will look at the keyword any. It means what? Any means universal, right? Every, any, all, for every, these are universal, so it will be a universal statement. And then for all real numbers R and S, this will be, if R and S are rational, this will be your hypothesis. Means if R is equal to A over, again you will use different variables for both the rational numbers. And what is the condition? You need to know the condition also. Denominator is 0, and second rational number is this, where, what is the condition? This. Okay. So this is the hypothesis. Okay. These definitions you will be the starting point of your proof. Now what you have to actually prove is that R plus S is rational, along with the this. Okay, this is what has been done over here. Okay, so R plus S is rational. Take the definitions from the hypothesis. Okay, now you know that A is integer, B is integer from the definition here. If you look at as a quotient of two integers, so you know from the definition that both of these are integers. Okay, so keep that in mind. A is integer, B is integer, C is integer, D is integer. B is not equal to 0, D is not equal to 0. These conditions. After that, you will substitute these definitions in the conclusion part that you have to prove. Okay, so this is R and this is S. You take the sum of these two, and then here this was what I was talking about, that you will need some mathematical knowledge. Some here you are using basic algebra. Okay. Make the denominator same. This is what you get. Okay, and after that what you can do is, you know that all of these are integers, so you can assign them, you can simplify, assign them to some other variables that will also be integers. Why? Because we know that sum of the integers are integers, product of integers are integers. So here you see, we know that all of these are integers individually, their product will be integer and their sum will be integer. So we can simplify them further. So you can simplify, you can assign A, D plus C, B to any variable that will be an integer, and then you can take the denominator, and we know that B is not equal to 0, D is not equal to 0. When both of these are not 0, it means their product will also be, will not be 0. So you can assign that to some other variable where this is also not equal to 0, because both of these are not equal to 0. Okay, and here this is based on the zero product property. Means that if A and B, any two variables, any two numbers, they are not 0, their product, both of them are not 0, then their product will also not be 0. Okay. And then you can simply show this whole as x over y, where, okay, this is the representation of what you had to show over here, this one. Okay, rational. This is the definition of rational numbers, this one. Clear? Understand? Yes? Okay. Any questions? No questions? Then we will move on to the next concept, next topic. Divisibility. Okay. Now, what divisibility is in terms of the symbolically, you need to have at least two numbers, two variables for divisibility, right? Something needs to be divided by some number needs to be divided by or be divisible by other. So you need at least two. So you are taking two variables. If n and d are integers, so both of these are, first point is both of these are integers, then when do we say that they are divisible? N is divisible by d if and only if n equals d times some integer and d is not equal to 0. What does it mean? We can write it in different, first let's go through, we can write this one also. We can go through, we can write it down in n is divisible by d in some other ways as well. For example, it means that n is a multiple of, let's look at it in terms of a number just for just to show you an example. What does it mean is, let's say n is equal to 36 and d is equal to 6. Okay, so this is what is meant over here. Yeah, speak a bit more loud. N is equal to 36 and d is equal to 6. What does it mean? That n equals means this equals d times some integer. Okay, right? So 6, when you multiply it with some integer, it results in this n. Okay, this is the definition of when two numbers are divisible with each other. Okay, how else you can write in these ways? I'll show you. We'll look at it through the same example. N is a multiple of d. So here n is equal to 36, d is equal to 6. 36 is a multiple of 6, right? Or you can say 6 is a factor of 36, right? So same thing. Or you can say d is a divisor of n. 6 is a divisor of 36, right? 6. Or you can say 6 divides 36. Okay, this is what it means. Okay, so if you don't understand this, just plug in some values, but this is just only for your understanding. Don't use this method in writing down proofs. Okay, just to understand the concept, you can assign some values to these two integers and then understand these definitions through the values. Okay. And how do we write the last one? D divides n. Okay, in terms of this example, 6 divides 36. Okay, okay, clear? So these are all different ways of saying that n is divisible by d. Okay, so you need to know these symbolic representations to write down proofs again. And how do you write it? In the form of an existential statement. There exists an integer, for example, say k or any variable, such that n is equal to d into k and d is not equal to 0. Means this cannot be 0. Why? Because this will make n also 0. Okay. And the notation for when a certain number doesn't divide n, simply slash. Okay. These are the representations. This is the concept of divisibility. Let's look at some examples in terms of these ways. Okay, here. Is 21 divisible by 3? This is one of the ways, so it's correct, right? Oh. Next one, does 5 divide 40? Then this one is, how do you read it? Yeah, and then yes. Next one, this is 54. let's say this is 54. Yeah. Then please correct this one, it's 54, okay? Now here we will look at this concept of proving using application of divisibility, using the symbolic representation of divisibility directly in a statement that you have to prove. So I'll go through it first and then okay, let's go through it first. So the property is a positive divisor of a positive integer. This is the property, and the statement is for all integers a and b, you need to have at least 2 for the division. If a and b are positive and a divides b, then a is less than or equal to b. So this is the property, and this is what you have to prove. Now we are going to derive the conclusion, okay, over here. So by first we will the step will be the same. By definition of divisibility, you need to know the definition that there is an integer k such that, so this one this one in terms of the definition it is n, okay, and this one is d, and then this is some integer, okay. So if you look at the definition, just to translate, just to make it easier for you here in this example, this definition, okay. And then k must be positive because both a and b, we know that both a and b are positive, so k must also be positive, because if we are multiplying k with a, if it is negative, it will result in negative value. So it means we cannot have a negative k. A and b are positive, it means that the integer with which it will be multiplied with will also be positive. It must be positive, okay. And here this is based on a theorem. This also you can find in your appendix A. The theorem is that if AB, the product of A and B, is greater than 0, then both A and B are either positive or both of them are negative, okay. When both of them are negative, it is cancelled, okay, when you multiply. So that is why the result is still positive. That is why either both of them should be positive or both of them should be negative, which means that k should be greater than or equal to 1. Means this is the definition of positive integers, okay. Positive integers, we know that they start from 1. So k, which is the positive integer, it is greater than or equal to 1. Why we are writing it over here? Because we need to derive this. We need to reach this conclusion. That is why this one, okay. So we will take this inequality and then we will multiply, because starting from here, we have to reach this conclusion. We use this property of the positive integers and then add, multiply or divide, take some action such that we achieve this, okay. When we multiply both the sides by a, what do we get? This, okay, this is what we get. And from the definition of divisibility, we know that ka is equal to b, right? So we can substitute. So we are using the same methods, or we are taking the same steps of definitions of different types of integers and different functions, and we are also substituting, okay. So the steps that we are taking are same. They may be, the order may be different, okay. So here, by substitution, now this is we have proved we have proved the property of divisibility, that there for all integers a and b, if a and b both are positive and a divides b, then a is less than or equal to b, okay. This is how you prove the property for a given function or for a given expression or a given integer, using the directly using the definitions of whatever is given to you, whatever function is given to you, or whatever integer is given to you, and we substitute those definitions in the expression that we have to, or in the conclusion that we have to prove. Okay? Clear? Why are we multiplying by? We are taking this like because we have to derive. In this particular case, we have to derive. We have two different types of questions. One is we are deriving the conclusion. One is we are simply proving. Okay? That is why these are specific cases. We'll have another example in the later topic also. But in your usual tutorial questions, you will not be deriving, you will simply be proving using the definitions, okay? Is it clear? Yes? No? Clear? Okay. Next, we will look at floor and ceiling function. So for a floor, I'll go through the definition first. Given any real number x, the floor of x is denoted with this symbol, is defined as follows. So it is a unique integer. The floor of x is a unique integer. The condition is that x is less than n plus 1, and it is greater than or equal to n. Okay, what does it mean? All of these concepts are based they fall under the number theory. So let's look at it through number line. Let's say this is x, means this is the floor of any real number. How will you find the integer which is actually the floor? You will look at the smaller integer, means the integers on the left hand side on the number line. That will be the floor of x. If this is a because we are talking about real numbers, this is a real number. If it is, let's say, a decimal number, okay, and we have to find out its floor, let's say this is x, okay, the floor will be on number line the smaller integer, okay, closest to it. Okay, the immediate integer, the smallest immediate integer on the number line. Okay, so the floor for this 0.7 will be what? Integer 0. Okay, whole number we have to find. If x given to you is itself an integer, its floor will be the same. Okay, it will be 1. All right, so two cases. If it is decimal, then you will look at the immediate integer to the left on the number line. If the number itself is integer, then that its floor will be the same integer. Okay, and next is ceiling. Ceiling is opposite of that. If let's say this is the symbol for ceiling, and let's say this is the real number for which you have to find out the ceiling. Let's say x is equal to 2.5, and this is the number for which you have to find out the ceiling based on the definition on the number line. The ceiling will be, let's look at this example, the immediate integer on the right hand side on the number line. Okay, so what will be? Yeah, okay, so this will be the ceiling for this particular example. Okay, I'll go through the definition also. Given any real number x, so x could be any real number. Remember, this is not integer, it could be any real number, could be an integer, but could be any other real number also, like here you have decimal number. The ceiling of x denoted with this is defined as follows, that it is a unique integer n such that, so now this is the condition, x is greater than n minus 1 and it is less than or equal to n. So the same thing, okay, x is greater than n minus 1 and it is greater than or equal to n. Okay, Further, formally you can define it like this. So these two functions, three we have covered: divisibility, floor, and ceiling. All three of them have conditions. To recap, for divisibility, the condition is this. For floor, sorry, not this. Then for ceiling, okay. Oh. Okay. So these three functions, their symbolic representation you need to know. And let's look at some examples, how to compute floor and ceiling for given real numbers. So for the first one, floor for the first one will be, first we'll divide, what you will get, 0.4. So you have to find out floor for this, 5, yeah. Ceiling will be, for the second one, yes, third one, floor will be -4, because on number line on the left hand side, what you have over here, the next integer is -4, okay. Then ceiling will be -3, because here on we have to look at the right hand side, immediate integer, that is -3, okay. This is how you find out the floor and ceiling of given real numbers. Now there is a property, it's an apparent property, it's actually not a property, it means you have to disprove it. So you have to find out counter example. And these are specific cases, okay? These are not questions that you have to, statements that you have to prove. These are just some properties that you have to either prove or disprove special cases of those. That is why we are deriving, okay? So it's this example is similar to the property for divisibility that we proved, where we derived and we multiplied with a, etc. So similar over here also. This is, we already know that this is not a property, and we have to show the proof of this not being a property by giving a counter example, okay? So we need to find out one example where this is not equal to, left hand side is not equal to right hand side. So I have given one example. If you take 0.5 and 0.5 for both the variables, for both the both real numbers, and then plug those in. These are special cases. That is why we are either I'm repeating, we are either multiplying or we are plugging in some specific values of real numbers, okay? But in your exams, from exams point of view, will not be you will not have these type of questions, okay? This is just to show you the counter examples and how to derive, okay? So if we plug in the values on left hand side and right hand side, what do we get over here? 1/2 is 0.5, right? So this is not the same, right? Oh, this is 1. And what do we get over here? Floor of 0.5 is? Yeah, so if there is a question like that, the necessary information would be given to you. You don't have to, it will not be ambiguous that prove it. And the result that you get is that you are not able to prove it. It will not be like that. You will be given this piece of information that this is not a property, so you have to disprove it. Okay? So the concept that you need to know is that you have to show counterexample to disprove it. Okay? So then you can take, and also background knowledge is that that you need to know is that you have to show it for any real number. So you should know that you can take any real number that you should know, and then you can take any real number. Okay, you can plug in any real number to show the counter example to disprove a given statement. Okay, a property for any function. Is it clear? All these concepts clear? Now we have a similar example for proving a property of floor. So this is also an established property. How do we reach the conclusion? How do we derive this? We will leave it for later. We'll first go through, this is last topic for your today's lecture. We will leave it for later because this is derivation. We will first go through some examples of the type of questions that you will actually have in your tutorials. Okay. So let's go through. Let's look at, I showed you example of proving same types of integers. So let's look at different ones. For example, fourth one, the product of any even integer and any odd integer is even. Let's look at that. We have both types of integers over here. So okay. Oh. Okay. So now you have a simple proposition. The product of any even integer and any odd integer is even. The first step that you need to take is, what is the first step? Yeah? Yeah. So how will you rewrite it? Anybody? Yes? Yeah. Next, what will we write? Anyone? For all, yes? For all integers. You can take any variables. So, okay. Then, yes? Yeah. Okay. Now we'll start our proof. How will we start? Suppose this. Two different variable. Yeah. Okay. Now what you have to show is Next step. Yes? Next. Yeah, next step will be? Yeah. Wait a minute. This is, it should be odd. The product of any even integer and odd integer is. Yeah, this one. Still. There is some issue over here because we have to show it in this form. Yes. No, wait. This. Okay, 2. Yeah. K. Yes. Yeah. So next step will be take any because these all are integers. So next, thus, yes, yes. Next step will be, yeah, but you have to show it, right? The last, the concluding statement you have to show. You will take it, take this one equal to by definition. Okay? Okay? Okay. Next, sorry? Two kt plus k equals even? This one I told you, wait. See, this is from the assumption. You reached this point, right? 2 and then you had 2kt plus k, right? Okay. So this is from here in the beginning. We have the assumption, right? Oh. The first slide, that sum of integers is integer, product of integers is integer. Okay. So we know that if we look at this example that you have solved, we know that k is some integer, right? We know that t is some integer, right? And then we have 2 over here, right? So we know that is integer. And we know that from the assumptions that product of integers is integer, then sum of integers is integer. Okay? So to simplify it, we know all of these, this is integer, we can assign it to, to simplify, because we have to show this is already in the form of even integers, just to simplify, okay, to write a clean proof. Okay, where that is why we give the reason where x is even, integer. It will depend on what you have to prove. If you have to prove, and I told you what you have to prove is the conclusion part, right? So you have to check in the conclusion what you have to prove. In this, you had to prove that the sum of both of these is even. So it means you have to show in the form of definition of even integer. If it was that the sum of, let's look at that example also for odd. If in the conclusion it was that you have to prove that some expression is odd, then you will need to show in this form. Okay, we'll look at that also. For example, good job, both of you. Let's look at another example for odd. Fifth one, the sum of any odd integer and any even integer is odd. Okay, so now here, when you write it down in the form of, when you restate it, you know that you have to prove the conclusion in the form of an odd integer. Okay, so how? That is why you have to first identify what will be the hypothesis and what will be the conclusion. Conclusion will tell you in what form you have to prove, and hypothesis will give you the starting point, okay, for substitution. Let's look at one example for that. So now when you restate it, what do you get? The sum of any odd integer and any even integer is odd. So what will be the hypothesis? I will straight away go to the hypothesis and conclusion. What will be the hypothesis over here? If yeah, and yes, then yeah, yeah, correct. Let me, it's stuck. Okay, it is if n is odd and m is even. Now this is the hypothesis. You identify the types of integers because these will be your starting point. These are the ones that you will substitute. Then m is odd, or you can write it as n plus m is, take any variable, just simply write it in the form of its definition. Okay, so here you will have to show your proof at the end in this form, because this is what you have been asked to prove. Okay, now again you will start. I'll write it simply. I will not write down all the steps. So Okay. All right. Okay. So I'll start from the proof. N is equal to, yes? Anybody? N is equal to? Yes? Yes? And? Okay, we can take t here, and then here we can take x. Okay. Then what we have to show is in now this one we have to show in this form. Okay, so you have to take some perform some operations to show it in this form. Okay, so how can you do that? You can bring the like terms together. Then next step, okay, so you see already you have your expression in the form of definition of odd, right? So what you can do is let k plus t is equal to x. We know k, t, they are integers, some are integer, x is integer. Okay, so you see main steps are same, thus, and you can write where x is integer, some integer. Okay, thus we'll take this, n plus m is equal to 2x plus 1. Okay, so we have shown it in the form of the definition of the type of integer that you have to prove. Is it clear now? Yeah? Okay. You can try proving these other properties of even and odd integers, and if you don't understand anything, just let me know and I'll explain it to you. We'll stop here for today and continue in the next lecture with other proof methods. Let's take the attendance. Before that, for assignment, there are some group members who are either, I think they have withdrew, or they are not there. Okay, they don't come to class because of I don't know what reasons. So you can start working on your assignment without them. Okay, if you don't see your group member in your tutorial classes, okay, on regular basis, you don't see them, just start. Don't delay your start working on your assignment. Okay, and inform your tutorial lecturer. So we will try to contact, because they are still there in the attendance list, so we don't know. Okay, so just let your tutorial lecturer know and start working on your assignment. For students who have texted me on Teams, you will get your reply soon. Please wait. Okay, And any questions, you can just ask your tutorial lecturer. Okay. Please mark your attendance.